Thanks a lot for coming, and thanks a lot for the very kind introduction. I'm very happy to be back for the first time since I left. And I'll talk a little bit about, so the title is the Moiré, the Merrier. So this is a new type of quantum materials that I've been working on as a postdoc here, together with Leon Barling's KITP faculty. But this is also the topic of the currently ongoing program. So it's kind of describing both of these things hopefully in the next few minutes. As Lars mentioned, I was here as a postdoctoral scholar between 2021 and left this year in April 2024. And this was actually a picture that I took on one of my walks where I tried to get some inspiration. So it's really a beautiful environment. So now I've moved to the University of Cologne, which is an extremely different environment, as you can see. So Cologne has this very old Gothic cathedral, but otherwise the city of Cologne it doesn't adhere to the standard notions of landscape beauty, I would say. But one funny thing that I want to mention is that Cologne actually it has its own type of dialect in Germany. So the dialect is called Kölsch, which is also actually a beer. And in this local dialect, Kölsch, you would call Cologne Kölle. And I was walking around Cologne, and Cologne is actually a quite vibrant and young city, lots of students, very progressive, and I thought this has California. So people think of Cologne as California, even though the landscape is quite different. Okay, all right. So having said that, I now want to move over to physics, and before talking about quantum materials, I first want to get out the caliper and think about length scales in physics. So you've heard all different kinds of talks already here in this Chalk Talk program, and we of course think about different fields in physics, and we can roughly classify these two fields in terms of length scales. So there's extremely large length scales, maybe the size of our observable universe, which is 10 to the 25 meters, which is an extremely large length scale, right? So it's a 1 basically with 25 zeros appended to it. On the other hand, we have extremely small length scales. So the smallest length scales that people kind of think about in physics is the Planck scale, which is 10 to the minus 24 meters. So that's 34 meters. So that's a 0, and then you put a dot, and then you have 34 zeros until there's a 1. So it's an extremely tiny scale, right? So and roughly, if you now reduce the length scale here, maybe we can think about galaxies. So roughly here, the length scale is 10 to the 20 meters. And then we can reduce the length scale even further. You encounter planets. And at some point, the animation is not right here, but at some point, on the order of 1 meter, give or take, that's our everyday life, right? That's us, where instead of galaxies, maybe we think about golf balls or sailing. And then if we go to even smaller length scales, we think about atoms, 10 to the minus 10 meters. So this is the full atom, then the atomic nuclei, it's 10 to the minus 15 meters. And then inside the atomic nuclei, we actually have quarks, so subatomic particles, which are 10 to the 19 meters. So we have a whole wide range of different length scales. When we do physics, we actually think about different phenomena at different length scales, right? So if we talk about everyday life, Mark mentioned this already, we think about classical mechanics. If we think about the observable universe and galaxies, at some point general relativity becomes important. So classical mechanics here doesn't really work anymore for these large length scales. And if we turn to the other side here, if we think about subatomic particles, we should think about quantum mechanics, or if we go to even smaller length scales, we think about quantum field theory. And then at these very low energy scales, or length scales, we actually have no idea what's happening. So the key point that I want to make here is that basically on these different length scales, we should be thinking about different types of interactions, and different interactions become important. Right? Hand in hand with this also goes the fact that on these different scales, we use different types of theories. And we often call these effective theories for emergent phenomena. So that means that if you want to play golf, for example, you shouldn't really think about quantum mechanics, and you don't want to think about the individual atoms of your golf ball, but maybe you just think about classical mechanics. So having said that, for theorists, probably even knowing classical mechanics doesn't really help playing golf. Okay, so this is kind of the introduction. So I'm a condensed matter physicist. So in a condensed matter, our goal is to understand the basic properties of matter. So matter that we can touch or composes our world, basically. And so here we can ask very fundamental questions about basically the properties of matter and materials. So for example, why do some materials conduct electricity, but some other materials are insulators, right? So a copper wire, if you cut open wires, you might find copper. But on the other hand, if you look at like electricity poles, very often there's some piece of ceramic that actually prevents getting a current flowing between the pole and the actual wire, right? So that's an insulating material. Another question that we might ask is, what is the origin of ferromagnetism? So we all know magnets from our direct daily life, but how can we understand this given our basic understanding of basically the structure of materials? For this example of ferromagnetism, so one cartoon explanation would be, so if we consider, for example, this material neodymium, so this has a pretty complicated composition, and a piece of material is roughly composed of 10 to the 23 atoms. So that's a lot, right? And so these are arranged in a particular crystal structure, and now you could start basically and ask about, okay, what is happening in an individual atom? So we have this crystal structure, so here I'm showing, I don't know, 20 atoms, which are, again, just a tiny fraction of these 10 to the 23 atoms, but we can now zoom in and basically try to understand an individual atom. And so this individual atom, as I've mentioned earlier, so you have the atomic nucleus, and then you have electrons orbiting the atomic nucleus in various shells, and this is all basically almost chemistry here. But the key point is that each electron we can think about as a mini magnet. So each electron has actually a tiny magnetic field associated to it. So a magnetic dipole. And it turns out basic chemistry or quantum mechanics tells us that most of these electrons are actually paired up in these shells. So, and they like to pair up in a way that the magnetic dipole moment of each of these electrons exactly cancels. So that means that all of these shells here, these inner filled shells, where you have basically paired electrons, don't really contribute to the magnetic moment of the atom, and only a single or maybe two unpaired electrons give rise to a weak atomic field, weak magnetic field that is associated with this atom. That's basically the magnetic moment of an individual atom. So with the understanding that these atoms here have a small magnetic moment, dipole moment associated to it, we can now formulate a theory. And the interesting thing is that very often in physics, we can basically model these individual atoms quantum mechanically, but once we have derived a fundamental property, for example, that they are like tiny magnets, we can now come up with a classical model where we no longer need to think about quantum mechanics. So we basically are now thinking about a larger length scale, and in this larger length scale, we can almost do classical physics. So in this classical picture, paramagnetic material, so material that is not magnetic, would correspond to a state where these tiny magnets inside a atom, inside a solid are basically strongly fluctuating due to thermal fluctuations. And if you now lower the temperature at some point, the system, the interactions between these magnetic moments are in such a way that they would like to align in a ferromagnetic way. So that means that you have all these tiny magnetic moments, and the interactions in the system are now such that they want to all align in a parallel manner. So if you add them all up, so 10 to the 23 small arrows basically give you one big arrow, right? So small magnetic fields added up give you one large magnetic moment here. And so this is basically a cartoon picture of the ferromagnet, and the key point that I want to make, that is, once we've understood that the individual atom is like a small magnetic moment, we don't really need quantum mechanics anymore. So this is what we would call a classical state of matter.
So Urban, with my refrigerator magnet,
yes.
What's that material?
So your refrigerator magnet, that's a good question. That would mostly, I guess, iron or some ferrite material. So, and there actually this picture is a little bit more complicated because, so here these, what I've shown here are basically localized electrons, right? Your refrigerator magnet, this is at the same time a metal, so it conducts electricity. And then we need to come up with a slightly more complicated theory that for mostly didactic reasons, I didn't want to present today.
That's fine. That's why there's questions.
Yeah. Exactly, but this material neodymium that I mentioned in the previous slide here, okay, it's not written here, but neodymium, this is probably, you've all seen this, like if your kids play around with, or grandchildren play around with tiny magnets and they are pretty strong, that's usually neodymium. And in most of electric engines, in your washing machine, probably there's a neodymium magnet built in. It's not some abstract material. Okay, so we were talking about classical matter. Now I want to move over to quantum matter. So quantum matter is quite popular these days. So if you go to a coffee shop in downtown Santa Barbara, to Old Town Coffee, you can actually buy a quantum cookie at the coffee shop. I haven't tried that yet. Okay. So usually in physics, we of course only occasionally think about cookies, but more often we think about quantum matter as particular states of matter where the quantum effects are directly relevant for the macroscopic properties. So this picture that I was drawing, that basically you have these little arrows and they would all like to align, this picture completely breaks down. So you must not only take the quantum mechanical properties into account on the level of a single atom, but also you need to think about quantum mechanics when you want to describe how all these different atoms basically talk to each other and what global state they give rise to. Right? So it's very hard to take pictures, so there's some illustration here, this quantum soup. This here is one particular type of quantum material that I want to talk about later. You can see here already, this looks a little bit cold. So terms and conditions apply. So usually in our daily world, we don't really touch quantum materials unless you live in a physics lab. So usually we need to cool down systems to extremely low temperatures. So minus 270 degrees Celsius to actually see these effects. So, small caveat. Okay, I've been using the word quantum mechanics a lot already. Sorry? Okay, I've been using the word quantum mechanics already, a lot already. So just to say a few more words, quantum mechanics 101. So one fundamental property of quantum mechanics is that a system, so when we have a certain set of states that our system can be in, so some state and some other state, in quantum mechanics you're actually allowed to form superpositions of these states. So in a more formal way, you can say that the system is a sum of two states. This is completely contrary to our everyday life or what we normally think about. And it's also completely counterintuitive. So the best way to really think about this is mostly as a mathematical tool to describe the system before you do a measurement. And these numbers here, if you square them, basically tell you the outcome of a measurement. So if I now was supposed to measure what state my system really is in, this particular configuration would tell me that if you do this measurement often enough, 50% of the time you would find this outcome some state, and 50% of the time you would see this other state. So really this is basically specifying a particular type of probability distribution. It's almost like throwing a dice, and I'm just telling you that basically before you throw the dice, you should basically think about this type of setup. And this is, of course, something that maybe some of you have heard about already. So this is nothing else but Schrödinger's cat. Very often we say simultaneously dead or alive. And this is, of course, an answer to Shakespeare's problem. Okay, so now applying this to an electron in real space, we can say that we can take a superposition of the locations of an electron in space. So instead of saying the electron is at this particular position, I say, oh, I can sum up or superpose all these different types of positions of my electron. And because this is a type of probability distribution, it kind of gives rise to this kind of wave-like behavior of electrons. So in quantum mechanics, electrons are not really to be thought of as individual particles anymore, but rather we describe electrons in terms of wave functions that give rise to probability amplitudes. So this here is basically a plot of the probability of finding an electron somewhere. You can see here these ring-like features. Okay, so this is like a key insight from quantum mechanics. We have the superposition principle, and electrons are not really particles anymore, but rather we should think about them as some type of wave-like excitation. Okay, so this was my introduction to quantum mechanics. So now, let me give you a brief example of such quantum materials or quantum matter. And to this end, I want to first start with the Hall effect. So first, this is a classical phenomenon. Maybe some of you who have an electrical engineering background might be familiar with this. So the key insight from classical electromagnetism is if you have electrons moving, or electric charges moving in the presence of a magnetic field, they experience a force that is perpendicular to the direction of motion. So an electric field accelerates an electron in the direction of motion, basically, and the magnetic field is perpendicular to it. So suppose we have some type of current, the electron now will deviate from its direction of motion and gets a perpendicular force. So this means that over time, basically, here electrons accumulate on one of these boundaries, and as a result, you build up an electric field across the sample. So the electric field, or the voltage drop, is now perpendicular to the direction of motion. So we can formulate basically Ohm's law now with these different directions. So you have a voltage drop along the y direction, so this direction, in response to the current that has been flowing along the x direction. So the constant of proportionality that gives you this response, we call this rho xy, this is the Hall resistivity. This is proportional to the magnetic field, because this is kind of the key impact here, that the thing that has been driving the electrons actually to the edge here. Okay, so this is our prediction here, that the Hall resistivity is linear in the magnetic field. So to illustrate this graphically, if you would do a measurement in your system, find out the magnetic field and measure this guy rho xy, you would expect such a line. So this guy Klaus von Klitzing did these measurements, and what he found was something completely different, right? So at small B fields, you can see really this linear behavior. So this is roughly 1 Tesla. But if you increase the magnetic field, you see more and more of these very pronounced steps. This was an extremely exciting observation by Klaus von Klitzing, and he actually got the Nobel Prize only 5 years after. So usually in physics it takes a long time between discovery and Nobel Prize, but this was the clear-cut example here. So what is the origin here? The key insight has been that basically this quantization, so these step-like features, can only explain really within a quantum mechanical theory, right? So it's the key insight here. And what is the reason behind this? The reason is really that our initial assumption that these electrons behave as individual particles and we can basically think about them as billiard balls is not really valid. Instead, we think about the electronic wave functions, and it has been shown that basically these electronic wave functions have a certain shape. And it's a little bit of a convoluted way, but we can roughly think about them as pastries, right? So a standard German bread roll is a pastry that doesn't have a hole, ideally. A donut has a single hole, so these are Swedish kringles, they have 2 holes, and then of course pretzels have 3 holes. Right? So these are objects basically where the number of holes really determines a fundamental property of these objects. And if you now start deforming them a little bit, so if you, for example, sit on them, at least a little bit, the fundamental property, if they have 0 hole, 1 hole, 2 holes, doesn't really change. Right? So this is a property which we call topology, the number of holes, which is invariant under small deformations. And this property actually also determines these step-like features. So the topology of these electronic wave functions gives you these step-like features. This is an incredibly deep connection, which also gives you a sense of robustness, right? So these particular, which gives you a sense of robustness. So these individual steps here, they're incredibly robust against noise and also against small changes in B. So you really get these step-like jumps between these. This was another Nobel Prize-worthy discovery by David Staulis here, this mathematical connection between topology and these wave functions in the integer quantum Hall effect. Okay, so this also gives you another consequence. So our trivial vacuum, you can roughly think about it as a bread roll. Inside this quantum Hall system, we have this non-trivial topology, so a donut or a pretzel, let's say. But now, at the edge of these two, you somehow need to make a compatibility between them, right? Something must change. And the key insight here has been that at the edge between these where basically the topology of the electronic wave function has to change, you get these gapless or conducting edge states. On a classical level, you can think about basically circles. At some point, you cut these circles open, and instead of going in circles, the electrons now jump around these edges here. And these edge modes actually are very robust, precisely because they are protected by this change in topology. So they have basically you can do lossless or dissipationless transport along them. So zero resistivity. Okay, so this was one example of quantum matter. So more generally, we could ask, okay, why do we even do this, right? And one answer would be just for the same reason why we are studying black holes. So it's just fundamentally interesting, right? It challenges our basic understanding of the world. So there are beautiful papers that really make very intimate connections. So for example, in some of these magnetic systems, because of these quantum mechanical fluctuations are so strong, it turns out that instead of thinking about little errors, rather you should write down a field theory that looks like exactly the field theory that we use to describe light and how light interacts with electromagnetic particles or electromagnetic charges. So this is this paper that came out recently, quantum electrodynamics in a triangular lattice antiferromagnet. So this is like a very insightful and almost unexpected relation. On the other hand, quantum matter can also be useful, right? I've previously mentioned that these quantum Hall states have these conducting edge states. So we can do very robust transport along them. So encode, for example, information and transport it along here. And there are also ideas how to use certain kinds of quantum matter for fault-tolerant quantum computation. So usually quantum physics is very fickle, right? Small perturbations can have a lot of impact. But as I said, this topology, like the donut, doesn't really change the fact that you only have one hole. And similar things hold for knots, right? Knots don't really change if you perturb them a little bit. The idea is that you can basically perform quantum computing with these very protected quantities. And there's a number of companies that are investing heavily in quantum matter research, in particular Microsoft and Google. Even here in Santa Barbara, they have research labs that are devoted to quantum matter and quantum computing. Okay, so I've hopefully convinced you that quantum matter is extremely exciting. So how do we find it? So one way, historically, has actually been empirical discovery. So this quantum Hall effect, Klaus von Klitzing didn't really go along and say, oh, I'm going to discover the quantum Hall effect. Instead, if you read interviews with him, he says, I wanted to know how to make faster switches. So he was collaborating with Siemens, and was looking at some materials, and then more or less by accident he discovered these features. Similarly, also for high temperature superconductivity, Bednorz and Müller, they didn't really go about and say, oh, I'm going to find high temperature superconductivity. But they said, oh, you know, this material might be interesting. Our previous intuition has guided us towards this. So these days, we of course have very powerful computers. We can do computational simulations and catalog a lot of different materials and simulations. So it's a little bit of a more guided search, but still it's a lot of hit and miss, right? Empirical discovery. And I want to claim, and this is now the key point of what I'm going to say in the remainder of this talk, that over the past 5 to 10 years, we have been become witnesses to a paradigm change. So we are going away, at least in some fields, from this notion of empirical discovery, hit and miss, but rather towards the extremely targeted engineering of van der Waals materials. So 2D, atomically thin materials. And a key development here has been the fact that there are certain materials where you can use a scotch tape. So, for example, graphite. You can basically put this between two tapes of scotch tape and peel it off. And by doing this in a repeated manner, you can isolate atomically thin layers of graphite, which we call graphene. And we can actually do this with a number of different materials. So, for example, hexagonal boron nitride in a large class of semiconductor materials. This is now interesting because having these atomically thin layers can now play Lego with them and stack them back on top of each other and combine different materials which don't occur in nature, right? So you don't have to discover anything, but play Lego and build exactly these types of materials with these functionalities that you desire. Okay, and there's one particular interesting idea. So you can not only stack these two materials, so for example with such a hexagonal lattice, but you can also stack them with a finite twist angle. And you can see that by stacking them with a small twist angle, what you actually get is an interference pattern, right? So I get a new lattice, which is much larger than the atomic lattice constant here. And this type of new emergent pattern that we get, we usually call a Moiré pattern. It's a geometric interference pattern between two periodic arrangements. And these Moiré patterns actually have occurred in all over the place, even before physics, basically. So one historical way, so Moiré effects first came about actually in fabrics. So if you take 2 layers of silk, wet them, and then dry them again, you get these interesting Moiré fabrics. So Moiré is actually French for watered silk. So here's a picture from the 1860s where you can already see these type of Moiré patterns, not in such a regular arrangement. Also, if you go down to the Santa Barbara Art Museum, so I was there this weekend, there's actually a couple of artworks which have this Moiré pattern, or basically make use of this, especially in contemporary art. So this guy Anish Kapoor, who's an extremely famous British artist, he built this silver ball in Chicago. He also has this silver ball in the Santa Barbara Art Museum collection, which is at the moment not shown. He also has been playing around with Moiré patterns for quite a while. Moiré patterns are also used for navigation. So, for example, at Harwich Harbour in New York, in the UK, there's a particular sign or arrow where the direction of the arrow actually depends on which direction you look at it from. So if you look at it from the left, it tells you to go right. If you look at it from the right, it tells you to go left. And if you cannot hit it exactly center, it tells you to stay on track, right? So you can use this as a very clever navigational device. If you've been doing photography, so if you've been taking pictures of screens at concerts, you probably have also seen these types of patterns. So sometimes these Moiré patterns in photography actually also can be a nuisance. So if you Google Moiré, I tried this, the first few entries that you actually find are from photography sites. And they say, oh, what causes Moiré, how to avoid it, and how to remove it. We in condensed matter physics, we don't want to avoid Moiré, but as of late we've been embracing it. So this even gets you into the New York Times here. So in the following, I want to say a bit more about why this is so interesting from a scientific standpoint. So it doesn't only look nice, but it's actually useful. So for this, let's come back to this Moiré lattice here. And we can see that basically this Moiré lattice, I've mentioned this already, this has a new lattice constant, so the distance between these purple dots here is now orders of magnitudes larger than basically the distance between atoms here on this original honeycomb lattice. So for example, if you have a honeycomb lattice where you have a lattice spacing of roughly half a nanometer, and you pick a twist angle of roughly 1 degree, so this is much smaller than a twist angle of 1, you get an emergent lattice constant which is now 50 nanometers. That's basically 100 orders of magnitude larger, which is really unheard of. Typically, in condensed matter physics, if we grow different crystals, we realize different lattice constants, but they all stay in the same order of magnitude of a few nanometers. So this is interesting because now, if you remember back what I said in the beginning, if we have, in physics, we have different interactions, and the strength of these interactions depends on the length scales, right? So in a solid, if you think about electrons moving around, you have a kinetic energy that is just associated with the motion, and then you have an energy that is associated with the interactions. So now tuning the length scale now allows you to tune basically the energy scales between, or the ratio between the kinetic energy and the interaction energy scales. Okay, how much time do I have left, by the way? Am I running over time?
15 minutes.
Okay, all right. Right, so basically this now gives you a tuning knob, this twist angle you can now tune between kinetic and interaction energy scales in these systems. And then the following I want to show you 2 examples for this. So the first one is here an actual experimental measurement. So here they've taken tungsten diselenide and tungsten disulfide. So these are two semiconductor materials. This is the Moiré pattern that you would get. And what they did in these experiments is now start filling the system with additional electrons and measure the resistance. This is a quite remarkable plot already for us in condensed matter physics, because usually if we plot these phase diagrams where we plot the filling of the system, we rather get plots like this, where you have a few dots, and this is just reflecting the fact that very often to tune the number of electrons in a sample, ordinarily, you need to grow a new sample. So you typically need to change the chemical composition, and you need to follow a very complicated procedure to actually get a new material. But here in these systems, you can just tune the filling of such a system by, or filling of this material by basically applying a perpendicular gate voltage. So this is an extremely easy thing to do, and you can do this with very high precision. So this gives you this beautiful curve rather than just a few scattered dots. Okay, what are we looking at here actually? So at zero filling, the system is empty. You don't have any electrons, so the resistance is obviously infinite. So if the system is fully filled, you get a kind of trivial kind of insulating state, a trivial peak resistance. And now here the crucial insight is that also at half filling, so if you have exactly as many electrons as lattice sites, you get strongly peaked resistance here. And this is what we call a Mott insulator. This is an extremely non-trivial state where actually the strong repulsive interactions lead to a localization of the electrons. So if all of these red dots strongly repel each other, it actually becomes very unfavorable for them to move, right? So they mostly want to stay as far away as possible from each other and form this periodic arrangement and don't move anymore. Okay, so this is this Mott insulator of electrons. And remarkably, they can even take images of this. So again, this is completely unheard of usually in condensed matter physics because the lattice constants are so small. But now here, because we are talking about, I don't know, 100 nanometers instead of half a nanometer, you can actually take images of these types of configurations. But if you now remember back in the introduction when I was talking about magnets, I told you how like each electron actually has like a small magnetic moment, right? And I was thinking about these arrows and that they are all aligning in the same way. We can now ask the same question here now in this Moiré heterostructure where we have these localized electrons on these Moiré lattice. So what are the spins the local moments are doing? The first possibility here is now, of course, again, ferromagnetism, where you get a finite net magnetization. In the experiments, actually, they don't see this magnetization, so this can't be it. So a second possibility would be antiferromagnetism. So here, on the triangular lattice, these moments, or these arrows, are basically rotating in a 120-degree pattern. And if you now sum them all up, you can see that they exactly cancel. So you don't get any net magnetization, but still there's some notion that at each lattice site you have a small arrow pointing in some direction. And the third possibility, and this was actually work that I did here together with Leon, who's a KITP faculty, a grad student at UCSB, and Hongshen Jiang, who's actually visiting at the moment, who's at Stanford Accelerator. The third possibility is here that the system might form a quantum spin liquid. This is now something that I cannot demonstrate to you anymore in terms of arrows because it's an extremely non-trivial quantum state. So the state that we can roughly think about here is that on any given site we form a superposition state, so this weird quantum mechanical mix basically between two sites where they are in a simultaneous state of up and down and vice versa, right? Up, down, minus down, up here on this bond. And now on top of this, I take a superposition of all these different coverings. In this state, it's an extremely non-trivial state which doesn't have any classical analog, which is extremely exciting for us. This is what we call a quantum spin liquid, because these lots of fluctuations remind us kind of a liquid ground state. So this is the picture that we want to advocate, and so far we are still looking for someone to do the experiment, basically, or confirm this. That you have this Moiré lattice, you have localized electrons, and these localized electrons now form this quantum spin liquid state, this strongly fluctuating magnetic state. Okay, so now I want to forget about interactions for a moment, so this will be my last example. and just consider this bilayer structure of tungsten diselenide. So again, here we have this Moiré heterostructure. You can see here that we have these different stacking regions, right? There are these orange regions where it looks like that the two hexagons are almost on top of each other. And then here in those blue and green regions, they are translated by basically a small amount, right? So the center of one hexagon is on the top of a lattice side of the other hexagon. And we can now do one thing theoretically, and instead of thinking about electrons as particles, we can really think about the electronic wave functions and ask, in the system, forget about interactions, you just have electrons hopping around, but now quantum mechanically, what's the probability of finding the electron in the upper layer, and what's the probability of finding the electron in the lower layer? So this is what we call a layer polarization of the wave function. This can be plotted, and this green here means that the probability is exactly equal, so there's no net polarization. And if it's red, it's more likely to find it in the top layer. If it's blue, it's more likely to find it in the bottom layer. And you can see that you get kind of a whirling texture, right? So you can get these spins, which basically, or this layer polarization, which moves out of the plane and then moves back in. So it's like a whirl texture. That goes through the entire lattice. And there have been actually previous theories about these whirling textures. And if you study the motion of an electron, or the wave function of an electron, through such a whirling texture, you can actually convince yourself that it experiences a force which is perpendicular to the direction of motion. So this whirling texture gives you a force that basically deflects the electrons. I've been talking about deflection earlier, right? So I've been talking about this Hall effect where you have the Lorentz force which deflects the electrons because of the magnetic field. So here the same should happen, but in the absence of a magnetic field, just because of this internal structure of these materials. And this is what we would call a quantum Hall effect without a magnetic field. And people have come up with a new name, anomalous quantum Hall effect. And this anomalous quantum Hall effect has been actually discovered last year in twisted molybdenum ditelluride. So this is another Moiré material, and you can see here, they don't see all these steps, but they only see this quantized behavior that you have a very constant Hall resistivity, even if the magnetic field, so H here is 0, right? Okay, so this is a kind of a cool discovery, this quantized anomalous Hall effect in this material. This is also interesting for technological applications because these strong magnetic fields of 7 to 8 Tesla, they're extremely difficult to achieve in an experimental lab actually. So if you go to talk to Andrea Young here at UCSB, he will tell you like a Tesla is, I don't know, $200,000, right? So if you want to have 8 Teslas, you need to invest a lot of money, right? If you are zero Tesla, that is extremely exciting discovery to get this quantum physics here in this material. And now, this year, there has been a new experiment on a similar type of system at a slightly different twist angle. Now here comes the kicker. They find that the resistivity is not only 1 in certain regimes, but it can be also 3/2 and fixed at 3/2 or 5/3. So previously I've convinced you that, oh, you know, this Hall resistivity should be linked to the number of holes of this electronic wave function. So think about donuts or pretzels, 1 to 3 holes. But now here 3/2 or 5/3, that's not compatible with our notion of topology of these electronic wave functions anymore. So this is something where we need to come up with a new theory, a new theoretical framework, which actually, this is our understanding of this, that we need to combine the topology of these electronic wave functions and these strong interactions which can give rise to these interesting effects that I gave in the previous example. And this is actually one of the key themes of this workshop. So if you look at the conference program, there have been many talks on these fractional anomalous quantum Hall effects, which have been subject of this currently ongoing program. So just to recapitulate, to recall or to summarize, so these materials, Moiré materials, they are an extremely fruitful platform because it kind of allows us to study many body physics on new length scales, right? We are not confined to the atomic lattice constants anymore, but basically can change the lattice constant of our materials in a large manner. They're extremely tunable. You can combine different materials, you can play with the twist angle, you can change the filling. They And as I mentioned, you have this interplay of topology of strong interactions, which really requires us to think about new theories for these types of materials. With this, let me thank you for your attention, and I'd be happy to take any questions.
Good, you also have questions.
I'll start. I see the you use TMD a lot on the slide. What does that stand for?
Oh, yeah, maybe I didn't even write this down. It stands for transition metal dechalcogenide. So it's a bit of a mouthful. Yeah. So transition metal are a particular class of metals in the periodic table, and chalcogenides are another class of materials. So the Seifert, selenide, and this D means that you always have the structure metal and then two chalcogenide atoms. So you can see this. I don't know. I think I had a plot here, right? So you can see. So yeah, you have basically this red here. This is this transition metal ion, and these chalcogenide here on the honeycomb lattice. You can't really see this, but there's basically two of them, right? So this is looking at the other perspective. Yeah.
You said that it was really extremely tunable, but it seems like it would be very difficult to have. You're working with single layer or single atoms, right? And twisting it.
So what you do is basically you historically, what people have done is that you peel these layers off, so mechanical exfoliation. So you have now two atomically thin layers, so basically two sheets, and then now you just stick them back on top of each other. And by doing this many times, you get small variations, and you can measure basically the twist angle that you have, and then you get a large collection of different twist angles. This has been the historical way. But there are actually people now, because this field has developed so much over the past 5 years, there are people who have demonstrated that one thing that you can do, I don't think I have a slide on this in this talk, is that you fabricate such a heterostructure, and on the top layer you attach a little bar, basically, let's say of gold, just by nanotechnology that works. So you glue this on there, and now you take the tip of an atomic force microscope, so something extremely tiny, and you apply a small force against this, and because these layers are so weakly bound against each other, you can actually, like in a very, very precise manner, tune the twist angle. So it's really amazing, yeah. It's very fascinating, yeah. Yeah.
So your 2D samples, what is the area you're working with? How big is that sample area? Right,
so this is this is a little bit the dirty secret here. They are a little bit small, right? At the moment, these flakes, maybe so maybe you have 100 nanometer by 100 nanometer, 500 nanometer by 500 nanometer, but roughly. So this is the catch here. If I'm talking about a Moiré material, I'm talking about the system. So this lattice here. You can see this here, right? So this is basically one flake, and probably everything around it. It's not.
So it's 20 by 20 in the big league scale?
Yeah. So it depends a lot on the quality that you're looking for. Let me see. Yeah. So one point that I want to make is basically that here you have a lot. So you have a lot fewer of these big lattice sites than the small lattice sites, right? So typically we should say that maybe we have 10,000 Moiré lattice sites, whereas we have many more microscopic lattice sites. So yeah, but things are improving by a lot in the field. So I wouldn't be surprised if the growth, if these flakes actually grow. People manage high quality flakes.
Okay, thanks very much.
Yeah, thanks for having me.
I want to ask a tongue-in-cheek question.
Okay.
This is for the sake of our one of the candidates for president.
Oh.
What happens if you dip this in water?
Oh.
You know, like
probably it disintegrates.
No.
Yeah, even yeah.
It's totally tongue-in-cheek.
Thank you.